Hello everyone. We're now going to begin our analysis of the section on series. By definition, a series is a sum of ordered terms. For example, the sum 1 plus 2 plus 3 plus 4 plus 5, etc. up till 25 is a finite, what we call arithmetic series. 4 plus 2 plus 1 plus a half plus ... until 1 over 128 is a finite, so in other words limited, geometric series. 1 plus a quarter plus 1/9 plus 1/16 plus ... with no indication of a last term is an infinite series. So all three of these examples are series because they are the result of a sum of terms placed in one very particular order, sometimes with a pattern that you may have actually noticed in the three examples that are in front of you. Many series, as those displayed in the previous examples, are characterized by specific patterns. Such series can be presented in such a way that the exhaustive list of terms may not be necessary. We're going to use a synthesized form of notation to represent series, which we call sigma notation. So here's what sigma notation will look like. We're going to use a uppercase sigma. So this is a Greek symbol for S and will stand for the fact that we are doing a sum. So sigma for summation symbol. AK is the formula or represents the terms of the sum. K itself is the summation variable. So in other words, it's the term whose value is replaced by consecutive numbers. In this case, we would start counting from 1 and we would stop counting when K reaches the value of big N. So these are called the bounds of summation. So for instance, the sum from K equals 1 to 8 of 3K squared is obtained by replacing K by 1 and 2 and 3 and eventually by 8 and by adding the terms. So 3 times 1 to the power 2 plus 3 times 2 to the power 2 and eventually until 3 times 8 to the power 2. Here is a summation, so a sum where n is replaced by 0 until 5, and the formula that is used, or the terms of the sum, are obtained by calculating 10 times 1.05 to the n. So you see how the index n is indicated both in the summation and in the formula telling us where to replace it. So the values that we get from this sum are 10 times 1.05 to the 0, which is just 10, and then 10 times 1.05 to the power 1 and 2 and 3, and eventually we will get to the last term when the power is 5, and that would end our series. So in the other direction, here is a sum of terms. So here is an addition of terms that actually obeys a sigma notation, or obeys a form that can be represented in series form. So notice how every term is minus 1/10 of the one that preceded it. Minus 1/10 because of the alternation of signs. So 10,000 times minus 1/10 to the power m would be an appropriate way to represent all of the terms that appear. The first of which requires that we have m equals 0, so that 10,000 times minus 1 over 10 to the 0 fits with the first term. And when m is equal to 6, then we will get 0.01, which fits with the last term of the series. Here is a sum of terms, 4 plus 5 halves plus 6 thirds plus 7 quarters plus 8 fifths, ... until 203 over 200. Perhaps you can figure out the formula or the sigma notation for this series, for this sum. Observe how the numerator is always 3 units greater than the denominator. And although it's not written explicitly, the first term could have been thought of as being 4 over 1. So at the numerator, we have a value that is 3 greater than at the denominator. So here's an appropriate way of writing that series. So counting from n equals 1 until 200, replace into the expression n plus 3 over n those values. The summation symbol tells you to add up all of the individual terms that you get. Now there's not just one way of writing this expression because it also depends on where or what first value you want to attribute to your summation index. For instance, we could have counted from k equals 4 and had a denominator that is 3 units less than the numerator, instead of having a numerator that is 3 units greater than the denominator. So you can convince yourself by replacing k by 4 and then 5 and eventually 203 that this second sigma notation is equivalent to the first one and certainly reveals the same terms being added. So here are properties of finite series, which will probably make sense intuitively to most of you. These are properties that resemble those you would have seen, for instance, with limits. So a summation that is applied to a sum or a difference of terms can be split into two individual summations. Notice how the bounds of summation are the same. And if the original terms were added or subtracted, that operation is maintained between the series. This second property is called the scalar or the constant multiple rule. So if a constant is acting on the size of the terms of the series, that constant can be extracted. And rather than being included in every term, it will simply multiply the entire sum of the AK terms. Once again, the bounds of summation are unchanged. Now, infinite series are slightly special because they have no end value. We keep adding terms without a last number appearing in the series itself. So here's an example of an infinite series where every term is 1/5 of the one that came before it, and we add up these terms one after the next. So in sigma form, we could represent the series as being 5 times 1/5 to the power p. The letter that is being used makes no difference. So as long as you have a variable that represents the summation index, then that's fine. Could be p, could be k, could be n. Certainly here, one of the things you may observe is that the series is formed of terms that are of geometric type. So we have seen in the previous video geometric sequences where terms were listed. Here they're not just listed, they're also added along the way. But 5 would certainly play the role of the first term of the series, and every term is obtained from a ratio of 1/5 with respect to the one that came before. So 5 times 1/5 to the power p fits with every term. P equals 0 is used to make the term's size correspond to 5, and because of the 3 dots, then there is no indicated endpoint, so infinity would be the upper bound of summation. In this example, 2 minus 3 plus 4 minus 5 plus 6 minus 7, clearly there's a pattern here. Every term is growing in size by 1, but then again is also alternating. So we could represent this series by saying that we start counting from k equals 2, and then 3, and then 4, and minus 1 to the power k would guarantee the alternation in size of the terms, or in sign of the terms. It's very rare in our class that we will have to take arbitrary series and express them in sigma form. So what I would expect you to be able to do is, if the sigma form is given, for you to be able to expand it as a sum. The infinite series have the same properties as the finite series. So we can convert the sum or the summation of a sum or a difference of terms into individual summations, as long as both series actually have finite results. These are valid properties. Same for the constant multiple rule. We can extract a constant. So these rules apply as long as we actually do get sums from these individual terms. Otherwise, saying that something that is undefined cannot be said to be equal to something else that is undefined. Now recall that a geometric sequence is an ordered list of numbers where each term, other than the first, is obtained by multiplying the one that precedes it by a fixed value r that we call the ratio. So this is a video that came before the video on series, and it was called sequences. When these terms are summed, rather than simply being presented in a listed form, then we're going to call it a geometric series. So in the previous video, we used the notation with accolades to represent sequences. So for instance, A0 r to the k, with k equals 0 to n, would be a list of terms. So notice how we're simply listing out the terms in the order where k was replaced by 0, 1, 2, 3, and so on. And it's a finite sequence where we stopped replacing k by the time we got to n. In contrast to that, the second list that we have also goes through an addition of terms, and that is represented by the fact we have a sigma symbol. So we are doing the sum of the terms. However, the size of the terms are the same as we had in the previous list. Again, the contrast is really the addition taking place. So the first is called a geometric sequence, and the second sum is called a geometric series. Here are two examples of geometric series. In the first series, we have 3 acting as the first term, so that would be the A0 term. And every term that follows is 2/3 of the one that preceded it. So the ratio is 2/3. So basically the size of the terms is 3 times 2/3 to the power k. K equaling 0 corresponds to the first term, and when k is replaced by 4, then 3 times 2/3 to the 4 would coincide with the 16/27th, which is the last term of the series. In the second example, we have 3 dots at the end, indicating there is no stop to this addition of terms. This is an infinite geometric series. And again, observe how every term is minus 1/10 of the one that came before it. The minus 1/10 multiplier guarantees the alternation of signs. You could also use r equal to minus 0.1. And because the first term is simply a 1, it wasn't even explicitly written in the series itself. So the sum from k equals 0 to infinity of minus 0.1 to the power k.